Okay. Hopefully it's recording now. Right. So we talked about this idea of applying the general framework of f-tests to our two problems, which was one was the ANOVA, and then the other one was the one-way classification. I believe in this lecture I talked to I went over this in pretty good detail, so I'm not going to repeat it. The only thing that I added towards the end was the idea of ANCOVA. So we talked about ANOVA, which is called analysis, which stands for analysis of variance, and ANCOVA is analysis of covariance. And it may sound like it's a very complicated thing, because covariance, like we think of covariance matrices, but it's really, I think, it seems like it's not that big of a deal. It's like for historical reasons, it's related to this problem. Let's say in clinical trials, let's say if you do a treatment, so you have a bunch of patients, you give them a drug to some subset, and you don't give them drugs. Like the different subset, you don't give drugs, and so you have a response that you want to measure, and you model this as a in terms of whether they receive the treatment or not. So if you have this is post-receiving potentially post-receiving a treatment. So this could be 0, 1. So they either receive a treatment or not. So if they receive the treatment, your response will have mean beta 0 plus tau. If it doesn't, so treatment 1 gives you mean beta 0 plus tau. If treatment is equal to 0, then you get beta 0. And so this is an example. And if it was like this would be an example of like one-way classification with just one, or actually two groups. K would be two groups. And we're doing a particular encoding. I don't know if I talked about these briefly. So there are different ways of encoding the mean. So the last time what we did was this cell mean. So each group gets its own mean parameter, or you can use a reference group. For example, group 1 mean would be beta 0, and all the other groups would get beta 0 plus some delta. So the way that we did it last time here was each group gets its own mean. But if, for example, I call group 1, for example, beta 0, and then let's say beta 1 is equal to beta 0, and then beta 2 is beta 0 plus delta 2, and beta 3 is equal to beta 0 plus delta 3. This is a different encoding, and so it's a reparametrization, and you can write down the null that we wanted to test whether all the groups have the same mean in terms of these deltas. So it would be, in this case, for example, if you have just 3 groups, it would be equivalent to delta 2 being 0 and delta 3 being 0. And what happens is that the parameters are going to change the meaning of the parameters. So delta means like the difference from group 1, whereas before your parameters was like beta 2 was just the mean of group 2. Now you're just working with, let's say, beta 0, delta 2, and delta 3, rather than working with beta 1, beta 2, and beta 3. So the meaning of the parameters change, but the subspaces, the fitted values, the residuals, everything would remain the same, and that the f-test would remain the same. So however you parameterize, as long as you're testing for the same hypothesis, it doesn't matter. So this version that we're looking here at is this like sometimes called, I don't know, I would call it differential. Like you're basically encoding the difference. So that's kind of they call it dummy coding as well, I believe. It has different names, but the idea is that I'm gonna have a baseline which is beta 0, and under no treatment is beta 0. Under treatment 1 is beta 0 plus tau. So this is very similar to two-way classification, actually exactly two-way classification with a particular encoding. Um, if you just measure like the response after you do the treatment, this idea of ANCOVA is that we're going to also like include the variable pre-applying the drug or pre-treatment. So you measure everyone before you assign them to treatment or control, and then you measure them after. So you have both before and after, and most likely they're correlated. So the ANCOVA, the covariance is between these two. And including that Y base in the model improves your prediction and like reduces the variances and then the confidence interval. So that's the main idea, okay? And you can still, for example, test whether tau is 0, uh, which is saying that the mean of the two groups are the same, or tau is not 0. So you can do an f-test here, or you can actually do a t-test because it's just a single variable and they're going to be the same, actually. An f-test with a single constraint and a t-test would be equivalent. This is something that you can prove. But anyway, so that's ANCOVA. Okay, so in both cases, you still have the gamma in the model. So, but it's a very special case of what we discussed. You can either test the hypothesis of interest, which is whether the drug has any effect or not, using using either the t-test. This is like as one of the parameters. So you have 3 parameters now. You fit the regression model, and you can just test whether individual parameters are 0. That can be done by a t-test, or you can treat it as a particular general linear hypothesis, very simple general linear hypothesis, and do an f-test, and you get the same result. Okay? Does it make sense? If someone asks you what an ANCOVA is, now you know what ANCOVA is. So this is, for example, better than you try to model y post. This is like change from the baseline. I could try to look at the difference and then model it like this. That's another way. The above is better. So the above is, if I set gamma equal to 1, I get the below model. But the above allows you to fit the gamma, you get a different gamma, and this would reduce the variance. This is a better model than this, generally. Okay. And then if you extend this idea, there's this thing called MMRM, which is, again, if you look for jobs in pharma, like one of the, if you look at what you need to know, sometimes this comes up. It's mixed models for repeated measures, something like that. And the idea is that you generalize that model that we had before, but now you have multiple observations post receiving drug. So you have a baseline for each patient. So now you have patient I has this baseline, and then so at let's say week 0 is where nothing happens. So they haven't received any drug, and then at time 1, which might be week 2, and time 3, 2, 3, and these could be week 4 or 8, whatever. But just index them like this. So this is baseline, and then these are after treatment. So you get yi1 up to yi m, let's say, for patient I. And then you can write down a regression. So each one of these would depend, let's say, on time. So there's this decomposition of yt, and then there is a treatment effect, tau t, which depends again on time. This is the binary variable whether to receive treatment or not, and then plus again a time varying potentially coefficient of this baseline. Okay, so this would be a natural model to try to impose. The main issue is oftentimes these covariate, like the errors would be correlated because they're across time. Whatever is left over, oftentimes it's not good to assume that they're IAD across T. So that brings us to what we were going to discuss next, and I may talk about this model a little bit more. But typically you don't want to model epsilon it as a function of t. So between patients, the errors are going to be different, but because they're responses of the same guy across time, you would expect the errors to be correlated. And so our confidence intervals, things like this would not hold because you're under the assumption that the errors are uncorrelated, except the conformal prediction. So that would take care of this as well. But in the classical setting, if you want to do parametric confidence intervals, this model is not going to allow you. But this is a general, you can see this is a generalization of the model that we had before. If you just have a single time point, that would be like an ANCOVA model. But now you do it across time. It takes a while to think about why we have this form, but it's a very natural idea. Okay, so the y could depend on t, and so these coefficients are measuring the effect of these treatment and the post-baseline at different times. So you have different coefficients for them across time, and kind of this is a good model. Questions? We'll talk about this later a little bit if you have time. We'll move on. Let's do lecture 13. Okay, so what we want to move on is to this area where we basically discuss two things, as we'll see. So the two questions that today we're going to answer is, let me do a recap, then I'll talk about two questions. So, so far, let's say we did this linear regression under the assumption E1, which is saying that the noise is a vector whose covariance matrix is sigma squared I. Okay, it's a random vector, which means that the coordinates have the same variance and they're uncorrelated. Okay, and then we, under this setting, we calculate the covariance of beta hat, and then we saw that if we assume a little bit more, if we assume this E2, which is the normality assumption, then it unlocks all these interesting tests, like the t-test or f-test or these parametric confidence intervals. But today we're going to work under this assumption E1 for the most part. What I want to do is look at these two questions. So the first question is why we use OLS. Okay. Let's say there are other reasonable estimators. So what makes this special? Or is this least squares estimation idea? We motivated by least squares. Is this really a good idea? There was a little bit of statistics involved, so we showed or argued that it's also the maximum likelihood estimator. But even if you don't know maximum likelihood, you can just do least squares, and it doesn't have anything to do with statistics. So it's statistically, is it a good estimator? And then what happens, the second question is that what happens if I remove the assumption? So for example, if I have covariance of epsilon, which is not sigma squared I. The so-called, you can have correlated observations, or you could have this heteroscedasticity, which is unequal variance, as opposed to homoscedasticity. Okay, so we saw a general answer to this, so you could do conformal prediction. That would take care of this case, and much more. But let's say if we restrict ourselves to the parametric case, like classical setting, is there something that we can do? Okay. These are the questions. Does it kind of make sense? Hopefully by the end of this lecture, we would answer. We have answers to both. Questions? Okay, so I'm going to ask you a question. So let's try to answer this first question. So how should we answer this? So what is a good estimator? Let's say if I want to show that the OLS is a good estimator, what do you think I should try to show? We know some properties of this. So we already know that it has a good property, a certain statistical property of interest. We already know that. Anyone remembers what good we know about it? Or what is it that's good about it? Yes.
It's unbiased.
Okay, good. This is the perhaps the single thing that we know about it statistically makes sense. So the expectation of beta hat OLS is equal to the parameter that we want to estimate. So you're in that ensemble view again. Remember, there's this. If you're a statistician, you're looking at the ensemble of all possibilities. So under that ensemble, beta hat has a distribution. So it could vary, but on average, the expectation hits the target. Okay, so that's what is desirable unbiased estimator. So, but this can be achieved by many other estimators. So there are any number of other estimators that can achieve this. Unbiasedness is not, let's say, unique to the OLS. So if I want to show that it's a good estimator, what else do I? Yes.
To show precision.
Great. Okay. So what do we have at hand that allows us to measure precision? Or maybe let's see if you can finish. What's your name, by the way? Yes. Grant. Okay.
I don't know. Somebody else is guy.
Okay. So precision actually has a very formal definition in mathematics, like in statistics. It's a quantity in statistics which is called precision. But let's see. Norm of what? Okay, norm of this. Uh, is that a good quantity to try? What do I want about uh, what about the norm? So what do you expect us to achieve? Like minimize, maximize, is that? So the norm of this would depend on the norm of beta. So if beta, the actual beta is large, then if you have a good estimator of beta, the norm would be large. If beta is small, it's going to be small. So the norm itself is not going to tell me whether it's good. Like if it's big or small, it doesn't measure. How do we measure precision of the estimator? Yes. Good. Okay. Variance is like a precision. So I know that it centers around beta. So the distribution is centered around beta. If it's sharper around beta, it has a smaller variance. If it's more more spread out, it means that like as I go over the ensemble, I have more variability. Okay, so the variance is a good measure. And precision is actually the inverse of the variance. So if you have a variance, the parameter that is the inverse of the variance is called precision of a distribution. So what we want is kind of variance of beta hat OLS. We want to show that this is small. There is, however, a small issue in that this beta hat is a vector. It doesn't have a single variance. So let's say if it was even in the simple linear regression, we have two parameters, like you have an intercept, so it would be a two-dimensional. So what do we actually mean here? Like, what should I consider? I have like a variance for each coordinate. So let's say I have coordinate I has a variance, but I have a bunch of these. So in principle, I want to minimize all of them in a sense, but can you have a maybe suggestion of how to go about it? Do you have any idea of? This is harder. So minimize, or we want it to be small. Okay, but for this, I have a whole covariance matrix actually. It's not just the. So there's also like the correlation among the covariance. So how do we define? Any suggestions? So I can, for example, focus on one of the coordinates. I can say, okay, I'm going to look at beta hat 1, and then I'm going to show that among all estimators that, let's say, that are unbiased, I'm going to restrict to unbiased estimators. And we'll say among all estimators that are unbiased for beta, beta hat 1 of OLS has the smallest variance. Okay. And then the question is that maybe then what happens if I look at the second coordinate or something like that, right? So, but it's a reasonable idea. Um, is this good? Shall we do this or? Okay, this might be not easy to answer, but if you haven't seen it, like when you have a vector quantity, let's say if I have a vector parameter and I care about the variance, what I can do is I can generally reduce it to a scalar by a linear combination. This is a very general idea. So if I look at C transpose beta hat, this is like an estimate of C beta or C transpose beta. And it's going to be unbiased. And I can generally look at all the estimators of uh, beta and let's say I have another estimator of beta, which is beta tilde. This would be my estimate of C beta. And then I'm going to compare the variance of these for that particular C. And then I can vary C. So this would include the coordinates, but also includes more. Okay, so generally the general idea is that look at the general linear combination of the parameters. That would be a scalar parameter. Then I can ask the course what is the variance of the corresponding polygon estimator? Okay, if I do this and I can somehow show that for all possible C's, um, the variance of the resulting estimator is optimal, then I have a very strong result. This includes the diagonal case, but also, like, for example, it would show that beta hat 1 minus beta hat 2, the variance of this would be smaller than the corresponding variance of the other estimator. Okay, and this is the property that the OLS will satisfy. So the OLS has the smallest variance for these quantities among all possible. So what we'll show is like variance of C transpose beta hat OLS is less than or equal to variance of C transpose beta tilde for all vectors C. Yes.
Remember how,
It does, yes. Like, what part do you think is?
well, it just sounds familiar, but I know enough of the deep a little bit about it, so
So what did you learn about Kramer?
like if a estimator is unbiased and there was like an inequality, but basically if it achieves the Kramer-Rao bound, that's like the smallest, has the smallest possible variance.
Yes, that's exactly true. So Kramer-Rao gives you a lower bound on the variance of any unbiased estimator. And if it happens that the variance of your estimator achieves, like, is equal to that lower bound, then it can be smaller than that. So that's the like minimum variance unbiased estimator. The problem here is that it, like, the Kramer-Rao bound in our case would be, as you'll see, because I have a vector, um, I don't have a single variance, right? So one way to actually do um, Kramer-Rao in multivariate cases, exactly looking at these basically linear probes. You can call it a linear probe if you want. So we look at we take like linear probes of the estimator and look at the variance, and then kind of what you get is statements like this. Okay, um, and it turns out that, I mean, let's say this statement is equivalent to a statement about the covariance matrix. And if you write it in that way, that would be like the multivariate version of the Kramer-Rao. I'll talk about that. But if I want to write this in terms of the covariance matrix, what would happen? I can kind of get rid of C in a way. So C is a general parameter. So if you want to state this result in terms of the actual covariance matrix, can you relate these quantities to the covariance matrix? So what is this, for example? Can you write it in terms of the covariance matrix beta? Anyone remembers an identity? I'm going to give you some more seconds to think about. Yes. Yes, exactly. So this is our formula, right? So the variance is really also a covariance. So you can write this as a covariance um, of that scalar because the covariance matrix of a scalar and its variance are just the same thing. And so this is using that covariance of a linear transformation formula, right? So that side would be that, and the other side would be similarly C transpose covariance of beta tilde C. Okay, now I can rearrange. What I'm going to get is, what do I get? I get C transpose cov, let's say, beta tilde minus cov beta hat OLS C. This is bigger than or equal to 0. So if you move this to the other side and then just look at it in the other way, right? This is what I would get. Does that make sense? Just expand, and I just rewrote it in the other way, like switch the two sides and switch the direction of the inequality. Does it make sense? You just move one term to the other side and then pull out C transpose and C. So now, if you agree with this, what does this say? Does it look familiar? So this holds for any vector C. Does it look like, yeah?
Positively definite.
Not the two terms, but just a single way. Yeah. So this guy as a matrix is positive semi-definite. So this is equivalent to saying that cov beta tilde minus cov beta hat OLS is positive semi-definite. Okay, so this statement is equivalent if you follow the chain of equivalence. So this one doesn't have any C's in it anymore. So this is a clean way of stating this result. So if I show that the cov beta tilde minus cov beta hat OLS is PSD, then effectively I've shown that the variance of any linear probe of beta hat OLS is less than or equal to the variance of the corresponding probe of beta tilde. Okay? And this thing is usually written as cov beta tilde minus cov beta hat OLS Cayley bigger than or equal to 0. So there's this Cayley notation of less than or equal to or bigger than or equal to this is positive semi-definite. Okay? And then rather than writing it this way, you would write it like this: beta tilde bigger than or equal to cov beta hat OLS. That's how you'd write it. So in a sense, the covariance of beta tilde is bigger than or equal to covariance of beta hat. What does the bigger than or equal to mean? Exactly means the thing above. Okay, so this is the meaning of this statement is exactly that if you look at the difference is positive semi-definite. Okay, so you can kind of think about an order among covariance matrices. Just like you look at like variances, you say variance is bigger than the other one. We can say the covariance of beta tilde is bigger than or equal to the covariance of beta hat in this particular order, in the positive semi-definite order. It's not inequality in the sense of pointwise inequality or like coordinate-wise inequality, but it's inequality in the sense that when you say A is bigger than or equal to B, they're symmetric matrices. This means that A minus B is bigger than or equal to 0, and this is exactly meaning that A minus B is positive semi-definite. So you can treat positive semi-definite so-called cone as a way to define these inequalities. Okay. Okay, so that's what we want to prove. Okay, this is a fairly strong statement, and if you reduce it to a one-dimensional case, it would be just the variances are bigger, like the corresponding variance is bigger than the variance of the other one. But now in this form, it means that all the variances are smaller and all the possible linear combinations that you can form have smaller variances than the corresponding linear combination. Does it make sense? So that's the statement that I want to prove. Okay, let's try to prove it. So this result is going to end up being called Gauss-Markov theorem. And so to set it up, we have the E1 only now, no normality. You have the linear model, you have the zero mean errors, and you have the sigma squared I assumption on the covariance of epsilon. And then I'm going to look at a general linear estimator. Okay, so what I want, okay, I didn't mention this. So the thing that I want to prove is that Gauss-Markov. OLS is the best linear unbiased estimator. The blue on their E1. Okay, so it's unbiased and it's linear. And any other linear unbiased estimator is going to be having a larger covariance matrix in this sense. So it's best linear unbiased estimator. And then we'll talk about what happens when the E1 fails. So if E1 fails, then, for example, you have the covariance epsilon is sigma squared V, then this blue idea fails because it relies on the epsilon. So we'll see. Let me just prove the first statement. So I'm going to start with a general linear estimator. So beta tilde is A times Y. That is what it means to be a linear estimator. It's linear in the observation vector. And then what I have is that I want to assume that expectation of beta tilde is equal to beta. I want to assume it's unbiased. Okay. I'm going to look at the class where the estimators are linear and unbiased. So this in particular implies something about the A. So what does it imply? What is the expectation of beta tilde? Is equal to A times the expectation of Y, which is x beta. So if I set it equal to beta, what it gives me is that I want ax beta equal to beta for all beta, which means I want ax to be identity. Okay. So I need this constraint on A. Okay. So we're going to look at the linear estimator. We enforce the unbiasedness. I get ax is equal to I. OLS is one such estimator. So if you look at OLS is AY for this particular A. AOLS is X transpose X inverse X transpose. And we already know that it satisfies this constraint, but you can also verify. If I multiply by X, you get I. So now the question is that are there better choices? Can I find a better A? In other words, I can try to compute the covariance of beta tilde now and see if I can make a covariance matrix which is smaller in the sense that I mentioned than the covariance of beta hat OLS. Okay? So let's see what we have here. Yeah, so the Gauss-Markov theorem is saying that that's not possible. So among all linear unbiased estimators of this form, I mean, the linear part is kind of this, covariance of beta tilde is going to be bigger than or equal to the covariance of beta at OLS, which happens to be sigma squared X transpose X inverse. So, and then an inequality, like the inequality is exact only when beta tilde is beta at OLS. If it's anything else, it would be basically the covariance would be different. Covariance matrix would be different. So, and it would be kind of this inequality would be kind of strict in the sense that you can find a linear combination such that the variance is strictly bigger. Okay. And then the meaning I already mentioned. So the meaning is equivalent to this difference being positive semi-definite, which is equivalent to the variance of all linear probes kind of have this order. So how do we prove this? How should I go about proving it? I'm going to do the proof here. So I'm going to give you the first step, which is easy. So what I'm going to do is write A as AOLS plus some deviation. Okay, this I can always do. I can define D to be A minus AOLS. So pick a general A that satisfies this constraint so that the estimator is unbiased. And I write it like this. Then I'm going to look at the covariance of beta tilde, which is really covariance of AY. And I can expand this. So what is the covariance of AY? It would be A covariance of Y, right? You know this, covariance, A transpose. So what is the covariance of AY under our model? Covariance of Y is the same as covariance of epsilon, right? Because the x beta is constant, so covariance of epsilon is sigma squared I. This is where I use that assumption. So what I get is sigma squared A transpose. So far, I mean, we know this stuff. So let me try writing it here. Okay. And this is only just a definition. So let's say define basically D to be A minus A observation, then I have that equality. So I'm going to plug that in. So I'm going to plug it in. I get A OLS plus D transpose. And then you expand. Okay. So once you expand, you get the first term would be AOLS transpose. And you get two cross terms, and then you get D transpose. Okay, you get AOLS times D transpose, and then D times AOLS transpose, which I'm not writing. And so that would be an expansion. So far we are not assuming anything about A, right? Now I just want to use that assumption that I know that AX is equal to I by unbiasedness. So if this is equivalent to AOLS plus D times times X is equal to I, and I get AOLS times X plus DX is equal to I know that this is equal to I, right? Because the OLS satisfies that identity because it's unbiased. So this is equivalent to just saying that DX is 0. Okay. So now I have the expansion of covariance of beta tilde, and I also know that this identity holds for that D. It's equivalent to, to being unbiased. So the question is that what can I say about these cross terms? So you can guess why I didn't write the cross terms, because they tend to be 0 if you do it right. In the statistics, cross terms vanish. So why do they cross term vanish? Let's write it down. So cross terms vanish. For example, I have AOLS times D transpose, right? And this is just X transpose, X inverse, X transpose, D transpose, right? So why is this 0? So yes, you know it. Yeah. Yes, so this is the X transpose, which is 0, so it just makes everything 0. And the other term is similar. If you look at the other term, which is DAOLS, then so there will be DAOLS transpose, which is even easier because then you get DX. So what I get is really there's nothing here. So I get sigma squared AOLS transpose plus DD transpose. And so the first term is, what is this term, Yuan? That will give me the expression for the covariance of beta hat, OLS, right? So what is it? I mean, you can easily verify that it's this. We already calculated it, and then I have the D transpose. Okay. So if you just continue here, you get covariance of beta tilde is sigma squared. The first term would be covariance of beta hat OLS. And then I get the second term, which is sigma squared DD transpose. Okay, that's kind of the result that I managed to show. Okay, is this good enough? Are we done? So D could be anything as long as it satisfies this, but I already used that. But is this giving me the result that I want? So I want to show that this minus this is positive semi-definite. So I have to show that basically this is PST, positive semi-definite. Is this positive semi-definite? The answer is yes, because that's the theorem, right? So why is this positive semi-definite? Yes.
Like the transpose, which
Yes.
do that, you guarantee that all the elements will be positive.
No. So so when you do D transpose, you're guaranteed to be positive semi-definite, but you're not guaranteed that all the elements are positive, right? So you could have matrices that look like this but have negative elements. But you are guaranteed to, because positive semi-definiteness is trickier than all the elements being non-negative. But why any matrix that looks like this is always positive semi-definite? Anyone can argue. If they were diagonal, that would happen. Like you just get the diagonal elements that are non-negative, but there's no guarantee that when you do this for a general matrix, it's going to be always like entry-wise non-negative, but it's guaranteed to be positive semi-definite. You can use the definition of positive semi-definiteness. The definition is saying X transpose D transpose X. This has to be non-negative for all X. Is that true? X being a vector of the corresponding dimension. Yes. Yes. How should I write it as a NOR? Right. So let's call this Z. This would be Z transpose. So this is really Z transpose Z squared. Right? If I call this Z, then this would be Z transpose. So this is Z transpose Z, which is norm of Z squared, which is always non-negative. Okay, so this proves that any matrix I can write as D transpose has to be positive semi-definite by definition. Because when you write down this quadratic form, it's the norm of a certain vector. Right? And then sigma squared, you can easily see that this doesn't change anything. So if you multiply something which is positive semi-definite, I can multiply both sides by sigma squared and it remains positive as long as it's positive or non-negative. So this matrix is positive semi-definite. It shows that the difference of these two covariance matrices is positive semi-definite, which is exactly what I wanted to prove. And then you just backtrack and then it shows that the variance of any kind of linear contrast or linear probe is satisfying the corresponding inequality. Okay, so this is the proof of Gauss-Markov, which is fairly straightforward once you just set up the problem right. The only place that we use unbiasedness is this, which gets rid of the cross terms. And the only place where we used, I mean, we shouldn't say the only way, like, but we used, critically, we used the sigma squared I here and that step. Okay, so the two go together. So both are needed for this result. So if you have like a biased estimator, this need not necessarily be true. And if you have a nonlinear estimator, this need not be true. So linear matters. Nonlinear robust estimators can beat OLS for heavy-tailed errors, as well as like unbiased maybe. So you can always have like a biased estimator that has a smaller variance. It's not easy. It's not difficult to come up with a biased estimator. Can you come up with a biased estimator that beats this? Any constant estimator is going to be generally biased, but will have zero variance. Okay, so just pick a randomly selected, just even not random, just the vector all ones in the corresponding dimension. That would be an estimate of beta, but it's a very bad estimate. So, but has a zero variance because it's non-random. So bias helps to make this make sense. So the thing is about this nonlinearity. So if you assume E2, if you assume the Gaussian assumption, then you can show that not only among linear estimators, but among all general estimators that are unbiased, the OLS would be optimal in the sense that we talked about. And this is a consequence of the Kramer-Rao. Okay, so under E2, it will be best among all estimators, all unbiased estimators. So this is the consequence of Kramer-Rao. So you need the entire likelihood. You write down the likelihood, and you can calculate the Fisher information matrix, and you'd show that this really, this quantity is the Fisher information matrix. Fisher info matrix under E2. And that's the Kramer-Rao. The Kramer-Rao says covariance of any unbiased estimator is bigger than the Fisher information matrix in this matrix inequality, like matrix order. And because you have an estimator, which is OLS, that achieves this bound, so it has that exact covariance, it means that you can't go further down. Okay, so for this you need to be able to calculate the Fisher information matrix, which means the actual likelihood, and this happens under the Gaussian. But if you don't want to assume Gaussianity, you still get the result that we proved, which is among linear estimators. Okay, so this, for example, rule out the case if you have heavy-tailed errors, then you're not in the Gaussian regime, so potentially you could have nonlinear estimators. You can have more robust estimators that reduce the variance. Does that make sense? That's the connection to Kramer-Rao is via the Gaussian assumption. Does that make sense? Okay. Any questions about this Gauss-Markov result? So the question now is okay, so this hinges very, let's say heavily on this assumption, sigma squared I. And what if it fails? In real world, it could fail. For example, if the variances of the noise are different, it could depend on the covariance. This is possible. And it could be that you're dealing with a time series, as I mentioned, that kind of MMRM setting. Time series often have correlated noise. So if you're here today, tomorrow you're going to be very close to this point, not, for example, down there. So they tend to vary continuously. So there's going to be generally correlation or covariance, non-zero among consecutive errors. Or you could have repeated measures again, like clustered data. So things that are in the same cluster would have like similar errors. Or this MMRM setting, which is an example of the time series or the clustered idea. So you can like model these in this more generalized framework. So we still assume that the errors are zero mean, but the covariance of them is sigma squared v. Let's say for some known v for now. Okay, so the v is known, but it's a general matrix. So bad news is OLS, although it's still unbiased, is not going to be the best like linear unbiased estimator anymore. And in fact, if you do these covariant, like what is called the confidence intervals, the t-test, the f-test, they all are going to be wrong in the sense that your coverage, for example, for confidence intervals are not going to be the things that you set. Especially if you have correlated errors, you tend to underestimate the variance. So the variance would be larger generally. So your confidence intervals would be smaller than they should be. That's the bad news. The good news is if I'm in the setting, there's like an easy way to fix the whole thing. Okay, so this idea is I can do some sort of a rescaling or the so-called whitening to transform the problem back to the case where this is the identity after transformation. And then there I know that the OLS is optimal, so I do OLS in that transform domain, and then it tells me what I should do in the original data. Okay, so let's see how this works. So this leads to the idea of generalized least-squares or GLS, which is really OLS in disguise. So the way we do it is we can decompose V into like something like LL transpose, or if you have gone to the TA in one of the early lectures, because V is going to be positive semi-definite because it's roughly the covariance up to a scale of a random variable. It has to be positive semi-definite. It has a square root. It has a symmetric, for example, square root, which is called, let's say, V1/2 or V square root, which is something that if you multiply by itself, it gets back V. This, for example, you can calculate using the spectral decomposition, if you remember. We can use this, or we can use it non-symmetric square root. This is an example of a non-symmetric. So a matrix that allows me to write like LL transpose is equal to V. You can think of it as a non-symmetric square root. Okay, it's almost like LL is equal to V, but the transpose of it. So there are many ways of writing a positive semi-definite matrix in this form. In particular, if V is invertible, there's this thing called Cholesky decomposition. How many people have seen Cholesky decomposition? Oh, one person. So what is the Cholesky? Oh, two. What is the Cholesky decomposition? One of you wants to enlighten us. What is the Cholesky? So it's like a decomposition of this form where L has a particular form. What is that particular form? Or lower triangular. In this case, it's, yeah, so it could be upper triangular or lower triangular. But let's say L is lower triangular, which means that the L transpose is upper triangular. So it's a matrix that has zeros above the diagonal. So you have things on the diagonal, but something is going on below the diagonal and on the diagonal, but above it, everything is zero. Okay, so that is always possible for a positive definite matrix. It's a very useful decomposition, especially if you want to solve a linear system, for example, involving a positive semi-definite matrix. This is what you can do, and then the problem reduces to kind of like a recursive or forward-backward approach. You solve two like simple linear systems. But anyway, so this is fast. This is faster than doing. You can also use this if you go through the argument. It doesn't matter what we use here, as long as it has this decomposition, like a square root decomposition. But Cholesky is fast, and it turns out that L is going to be invertible if V is invertible. For a triangle, like a lower triangular matrix to be invertible, it's enough that the diagonals are non-zero. In this case, they are going to be positive as well. So they're going to be all positive. So I have this, let's say, decomposition. for phi, which is easy to compute numerically. And then what I'm going to do is I'm going to transform my linear model by applying L inverse to both sides. Okay, so I apply L inverse to y, and I call it y tilde, and I apply L inverse to the other side. I call L inverse x tilde, and then L inverse epsilon, I get epsilon tilde. Okay, this is doable, and what I get is, see, what we get is a new system, which is like y tilde is equal to x tilde, the same beta, plus epsilon tilde. Okay. So both y tilde and x tilde are known because we know L. By assumption, we know V, we know L, and then we know y and x. And epsilon tilde is some new transformed noise vector. So let's look at the covariance of epsilon tilde to see why this transformation is useful. What is going to be the covariance of epsilon tilde? This is like L inverse epsilon. We apply our well-known formula. Yes.
Yeah, you just take out the L inverse, so it's L inverse covariance, yeah. L inverse transpose.
Transpose, yes. And then the transpose and inverse kind of commute. So really L inverse transpose is the same as L transpose inverse. And sometimes you can just write it as L minus transpose because the order doesn't matter. I'm going to write it that way. So this gives me L inverse covariance of epsilon is V, I sigma squared V by assumption. And then L negative T. Okay, and then pull sigma squared out. I'm going to rewrite V as L transpose and then L negative transpose or inverse transpose. Okay, and then look what happens. So what happens here? So what is this? L inverse L. That will be I. This one is also true, like I. So it's really, you started L inverse transpose, so you can write it as L transpose inverse. This is really also L transpose inverse. So it's the inverse of L transpose, so multiplied by L transpose, you get I, so you get sigma squared I. So the effect of this transformation is to make the covariance of epsilon tilde look like the desired form. This is called whitening or decorrelation if you want, but whitening because the kind of noise is now white. So uncorrelated and has equal variance for all coordinates. So is this good? It is great, actually. Why is it great? Because now I have a linear model, right? With a noise vector that satisfies the assumptions that we started with, and we know gives me like optimal OLS. So now in this model, the OLS would be optimal. It satisfies the Gauss-Markov, so it has the smallest variance. So if I compute beta hat OLS in the new model, in transformed model, I get x tilde transpose x tilde inverse x tilde transpose y tilde, right? So this is the OLS in this new model. So this is guaranteed to be unbiased because it's a linear model, the usual linear model, and it's going to be having that property because in this model, any unbiased estimator of beta will be beaten by this guy in terms of the variance. Okay, and then you can rewrite this in terms of, so that's the OLS in the transform model, but if you rewrite it, I just can plug in what these guys are in terms of y and x. If you do it, you can get this form. You can just put back together LL transpose, and you get x transpose V inverse x transpose V inverse y. So this V inverse just comes in between these terms. Okay, so this new estimator that we created happens to be the OLS in there, like the right-hand model, and so it's the good estimator. So it's called the generalized least squares estimator for this model, and I can port everything I know about OLS via this transformation to this estimator. For example, I know, for example, what is the covariance matrix of this. So covariance of this would be the same as the covariance matrix of the OLS in the, let's say, beta hat OLS in transform model, which happens to be like sigma squared x tilde transpose x tilde inverse. And if I write it in terms of the original x, I get x v inverse x trans, or the other way. Something like this. X transpose v inverse x inverse. So once you plug in x tilde, you get that. Then you can basically compute the residuals here. And then when you compute the residuals, you also get an estimate of s squared. So the unbiased estimator of the variance would be e tilde squared divided by n minus p plus 1. And this e tilde you have to rewrite, if you want, you can rewrite back in terms of the residuals, original residuals. So this is going to be I minus, let's say, h tilde y. This is the hat matrix in the new model. And this involves x tilde, like x tilde transpose, whatever. So you just unpack it, and it would be something in terms of x and v. So you get an unbiased estimator of the variance, and you can compute the confidence intervals and the t-test and an f-test. Whatever you're going to do, you can just do it in, let's say, usual way in the transform model, but you can also translate everything into the original x and y and v. And so if you do it, for example, let's see if I have the statements here. Yeah, so for example, this is going to be unbiased. The covariance would be this, and then the sigma hat squared, or you can call it like s squared if you want, GLS. It turns out this is the e tilde squared. And so if you unpack what it means, that would give you this. Okay. So roughly we are basically taking inner products if you look at it carefully. So GLS really, this is like a geometric picture. It's like an orthogonal projection of y onto Lx in a new inner product. So if you define an inner product between two vectors as A transpose V inverse A, this is a generalized inner product. Rather than a Euclidean inner product, then you can prove that this is actually a projection. So projections depend on inner products because they depend on length. And so you define inner product. From the inner product, you get the norm and the length. So the projection is the thing in this space that minimizes the distance to the original one. So if you measure the distance in this norm, the norm induced by this, then you can think of it as just projecting onto like all the geometric intuition carries, but with this non-standard inner product. Although you don't need to worry about this, you can just transform everything, and then you have the OLS with the transform. But this is an interesting geometric picture. Okay, so this result apparently is called Aitken's, and I didn't know this until recently, until some basically, but apparently this is known as by this guy. It's worth mentioning, and so it's nothing but an application of the Gauss-Markov to the transform model. Okay, so under the generalized model with V known and positive semi-definite, beta tilde GLS is blue, best linear unbiased estimator. In this sense, so any other linear unbiased estimator has covariance which is bigger than or equal to the covariance matrix of this guy, which is exactly this quantity. Okay, so if you understood Gauss-Markov, this is right. Just immediately follows by applying to the right-hand data. Okay. So this unlocks a lot of applications. Like a special case, let's do a special case first. So in the special case, you have V diagonal. So let's say it's a diagonal matrix. You have a bunch of variances, sigma squared, I sigma squared. And then let's say divide by sigma squared, because then sigma squared, basically V is sigma squared 1 up to sigma squared. And if you look at V inverse would be a diagonal matrix. And the diagonals, let's say, are Wi's. These are going to be these weights, sigma squared divided by sigma squared I. And if I write down the beta tilde GLS, it would look like this. So V is W. In this case, we can call it weighted least squares, because this, you can easily show that this solution is really the argument of this weighted least squares. So these weights are exactly these W's that appear on the diagonal of V inverse. And so if Wi's are 1, this is just the least squares cost function that we minimize to get the OLS. What this is saying is that in the diagonal case, we can equivalently like write down the objective. The objective would be this weighted version of these squares. And it makes a lot of sense because what you're doing is, let's say, if you have high variance observations, sigma i's are large, then the weights are smaller. And so you're downweighting those observations. So because you know that they're high variance, so you don't want them to influence the cost function as much. If they're low variance, then sigma i's are small, this is large, so you upweight those samples. So you adaptively like rescale the errors so that they kind of balance out, so that high variance ones don't basically overwhelm the cost function. And then the low variance ones are kind of, basically you want to put more of your budget on low variance ones rather than high variance. So that's kind of intuitively what it's doing, and it makes a lot of sense, and you can show that they're equal. So if you solve this, this is really like y minus x beta transpose w. And you can do it for the general least squares as well. So that's minimizing this, would give you the VLS. Okay, so if you do it, for example, here we have a simple linear regression with increasing variance, error variances. So these sigma i's are functions of xi's. Then wi would be proportional to 1 over sigma i's. And you can see here, I'm showing the beta hat, the distribution of beta hat. For the OLS, the standard error is 0.1. For the VLS, like WLS, beta least squares, the standard error is like 0.7, like 0.7. And then you can see the variance is smaller. It's a better estimator of beta. Both are centered at the same point, which is the true beta. They're unbiased, but WLS is lower variance. Okay, let me just mention this, and then maybe we can just maybe 2-3 minutes or 2 minutes. So we so far assume that we know V, but in general, you don't know V. And oftentimes you can try to estimate V. And in some cases, it's really easy. For example, in time series, oftentimes you have these time series models. Let's say I impose a so-called AR1, which is called autoregressive with order 1, which is very common time series model. So let's say epsilon t depends on exactly the previous step by factor rho, plus something like this is the like a constant times nu noise. So ut is standard normal with mu 0 and variance sigma squared. If rho is 1, then epsilon t is going to be equal to ut, so that would be the IID case. But if rho is non-zero, then there's dependence. And you can show that the covariance matrix, so basically covariance of ST and epsilon t would be sigma squared rho of the difference. This gives me a topless structure. Can show, but what I can do, I can estimate the rho. Well, for example, I can fit the OLS. I get the residuals. If I get the residuals are estimators of these, so I can regress E hat T on regress on E hat T minus 1. This is a regression problem. If I do this, this is an approximation of the errors. So I can regress this on the other one and then get rho. Rho would be like it's like a zero intercept model, a simple linear regression. I get rho hat, which is this. Okay, so that's my estimate. And then I plug in into, I know this form, I plug in into the formula, I get this estimate of v hat. And now I can use my GLS. So if I do the GLS, for example, what you get is, okay, so what you get is this plot. Just let me explain this plot and then we're done. So here you can see like the confidence intervals, and the naive OLS kind of misses about, like covers 22 out of 42. This is like a simulation with rho is 0.7. So it's like, and you can see here at rho is 0.7, the coverage is like kind of drops to half. Whereas this is called feasible GLS because now we can actually implement GLS. The feasible GLS is like much higher. So most of the intervals still cover. And so because you can see like the OLS has a smaller um, length of this confidence intervals. Okay. So I think that's good for now. Next time we'll come back and I'm going to maybe spend a little bit of time discussing this and then move on to the next topic. Okay, thank you very much. Excellent.